today we shall consider some generalized versions of the Turing machine which are equivalent to the basic model. Actually, when we were considering as a input output device, we had a two-way infinite tape. When we looked at it as a accepting device, it was one-way infinite, left hand was fixed. Are we justified in doing that? Actually, it does not matter whether you consider it as two-way infinite or one-way infinite, you can do the same thing. So, the first thing is you make the tape two-way infinite for acceptance. Two-way infinite tape is equivalent to one-way infinite tape. How do we prove that? You have a two-way infinite tape and the input is given here. When you look at it as acceptance, you start from here. After making some moves, it goes to a final state and accepts. You can make use of some blank cells in this side, you can make use of some blank cells in this side also. But if you look at it as a one-way infinite tape, the input is given here. You will start from here and you can make some moves and then accept. If the Turing machine ever tries to move of the left end, then it will halt, it will reject the input. You should not move off the left end of the tape when you look at it as a one-way infinite. Now, you can very easily simulate a one-way infinite tape with a two-way infinite tape, is not it? Only thing is, when the input is given, you make a marker here on this cell, and so then you just simulate it as you behave here, you can just simulate it. If at all it tries to move off the left end, it will go to this marker cell, then you have to reject, that is all. To simulate a one-way tape by a two-way tape is very easy. Now, how do you simulate a two-way tape with a one-way tape? Now, if you have a two-way tape, you can make use of some cells here also. For that, you take a tape which has got two tracks. Consider a one-way infinite tape which has got two tracks. If in the two-way tape at some time after some moves you started at this position, say A0, some symbols are there A1, A2, An. You might have used some symbols A minus 1, A minus 2, etc. here. Right, you start, initial position was this, then you have made use of some cells here, input was here, then you could make use of some blank cells here, you have made use of some blank cells to the left also. Now, in that case, how do you simulate it with a one-way infinite tape? You start with this A0, A1, whatever was the input, suppose the input was say small A0, A0, A1, An. The input will be here like this, the lower track will be just blank at the stage. Then after making some moves, see when you want to first move, say A0 was here originally, it was replaced by capital A0 and you move right, this will be replaced by A0 and you move right. But first what you do is, whenever you make the first move, print a symbol, some marker on the lower track at the first cell. Then after some time, this is the content of the tape, say after some time, these symbols A0, A1, An will be there on the first track, A minus 1, A minus 2, these symbols will be there on the lower track in the reverse order, A1 this way it will be like this. So, at some time you are reading a symbol here, you will be reading that symbol here, but you will be reading from the upper track only. So, whether you are going to read from the upper track or the lower track, that information you have to keep in the state. In the original machine, if Q is the state, in this machine you will take QU as the state or QD as the state, upper track, QD down or something like that, or you can say QL, lower track. So, the state will keep the information. We have earlier seen that you can make use of the state to store some information. Here you are making use of that to store the information, whether you are going to bother about the symbol in the upper track or in the lower track. So, in this case, suppose you are going to read a symbol A, that is here, then after reading that you move right, means here also you will move right. If you move left, means here also you will move left. On the other hand, if you are reading some symbol here, say some A, then after making the move, if you move left, here you have to move right. If you move right here, you have to move left here. Okay. So, if you are reading the symbol, this symbol, the tape head here will be pointing to this. Now, if the move is to the right, in the state you will change it, whatever this, when you are reading here, the state will be either QU or QD, whatever it is. Then if the move is to the right, the state will change to some PU. If the move is to the left, then the state will change to, move will be right, whatever you read here, the next move will be to the right. But in the original one-way tape, I mean in one track, if you move right, then the state will change to PU. If you move left, the change will state will change to PD. You are reading this in state Q and you are going to change to state P, and move right means here from QU you will change the state to PU. If you are going to move left means from this or this you will change the state to PD and move right. Okay. That way whatever happens in this portion you simulate in the upper track, and whatever happens in this portion you simulate in the lower track. So, two-way infinite tape can be simulated by a one-way infinite tape. So, it does not matter whether you take it as two-way infinite or one-way infinite, both are equivalent, the language accepting power is the same. Now, if this two-way infinite tape, an input is accepted in n moves, how many moves will this make? One-way infinite tape. For one move here, how many makes it moves? Just one move. Only one move. One move here is simulated by a move here. It may be move left or slight change may be there, but one move here is simulated by one move here. So, if this makes n moves before acceptance, how many moves it will make? This will also make n moves. The number of moves is the same. While printing this, you are counting this, printing the symbol, that the first move itself it can print and move, initial. Okay. Or separately you can use one move, that in that case n plus 1, but in the first move itself you can print and move, that does not matter. So, anyway it is n goes to n or n plus 1 does not matter, linear. So, number of moves is not very much affected by this simulation. The next is we consider multi-tape Turing machine. This is different from multi-track. We have already considered multi-track for Turing machine construction techniques. Now we are going to consider a generalized version. This Turing machine has a finite control. It has a finite control and several tapes. Say for example, 3 tapes I can take. You can have any finite number of tapes. Tapes cannot be infinite. It can have 1, 2, 3 up to k tapes. Now each tape is provided with a tape head. Each tape has a separate tape head. Multi-track, there will be only one tape and that tape is divided into several tracks and there will be only one tape head. It will be reading a tuple, that is the main idea. The tape alphabet is taken as a tuple, that is the idea of multi-track. Multi-tape Turing machine, you have several tapes, finite number of tapes. Each tape will have a separate tape head. Suppose it is reading this A, a symbol B here, a symbol. As an example, I have taken a 3 tape. A, B, C. Then the move will be like this, delta of Q, A, B, C will be some AR, BL, CR, something like that. The move will be something like this. The state can change and that should also be taken care of. That is, instead of A, it will print a A and move right. Instead of B, it will print a B and move left. Instead of small c, it will print a capital C and move right. So, the move depends on the state and each one of the symbol read, and the tape head can move independently. One tape head can move left, another one can move right, and each one will print another symbol on that. Okay. So, this is the way the moves are defined. Now, how is this equivalent to a single tape model? Originally we had this. So, how can you say that a multi-tape Turing machine is equivalent to a single tape Turing machine? You can simulate a multi-tape, of course, single tape Turing machine is a particular case of a multi-tape Turing machine, that is one way. The other way around, you can simulate a multi-tape Turing machine with a single tape, right. Simulate a multi-tape Turing machine with a single tape. The single tape, if you have k tapes here, it will have 2k tracks. So, here there are 3 tapes, so there will be 6 tracks. You can have infinite in both directions, does not matter. If so, the odd tracks represent the contents of the tapes. So, here something like A0, A1 something is there, that will be represented as A0, A1, A2, etc. At a particular instance, the symbol A is being read, right, And similarly here if you have some B0, B1, B2, that will be there in the third track, B0, B1 etc. It will be reading a symbol B at a particular instance. Oh, I am sorry, this is the fourth track. Third track will contain this B0, B1 etc. It is reading a B. And the fifth track will contain say the contents of the third tape, that is some C0, C1 etc. some it is reading C say at a particular instance. So, it is multiple track like this. The even number of tracks, they are all blanks except that one cell will contain a marker pointing the, I mean it represents the tape head position. For example, if A is being read, there will be X here, rest of this portion will be blank. Similarly, if B is read in the second tape at a particular instance, there will be a marker here in the fourth track, but rest of them will be blank. Similarly, there will be a marker here. So, how do you simulate one move of a Turing machine, multi-tape Turing machine with a single tape Turing machine? You start moving from left to right and then moving from right to left. You make one pass moving from left to right and make another pass moving from right to left. Start somewhere here. The state will have, here the state is q, say the state will be q, then there will be a counter here, there will be a, how many tapes are there? 3 tapes are here. So, there will be a counter which keeps the value 1, 2, 3 like that. Up to k it can have, from 1 to k it can store a number. What is the move? The move here is q a b c is a r b l c r. So, it has to remember that it is reading a from the first tape, B from the second tape, C from the third tape. So, it makes a pass, there will be 3 positions in the state to keep track of that. So, it makes a pass and then when it comes here it sees that there is a X in the fourth track. That means the second symbol is second tape, it is reading the symbol B. So, it will place that B here, then move again. Now, it sees another X here, that means the first tape it is reading the symbol A. So, it will put A. Whenever it is filling this, it is also initially it was 0. So, when it fills B, it has seen one symbol, so it will increment to 1. Then when it sees A, it will, this will increment to 2. Then it will move again, and when it sees an X in the sixth track, that means in the third tape it is reading the symbol C. So, that C will be put here, and now the counter reaches the maximum value 3. That means it has read all the symbols, right. Once it knows that it has read all the symbols, it starts moving, then move is determined now. Q A B C means it has to go to A should be replaced by A and move right, B should be replaced by B and move left and so on. So, what it does is, it starts moving like this and this C will be replaced by C, move is to the right, X will be placed there. Then it will continue moving left, and at this point again it is a move to the right, this will be replaced by A and this X will be placed here. Then it will move again, now this B will be replaced by B and X will be moved to the left. Now, while doing so, you can erase each symbol whenever it has been replaced, we can erase that also, and this 3 will be you will be decrementing that. So, when you at this stage it will become, after you do this it will become 2, after you do this it will become 1, and after you do this it will become 0. When it becomes 0, that means you have changed all the symbols and positioned the head in a proper way, right. So, that means you have completed simulating one move of the multi-tape Turing machine. So, one move of the multi-tape Turing machine you have simulated by making one pass from left to right and again a pass from right to left. So, how much time it would have taken, how many moves it would have taken to simulate one move. Initially, the initial position you can keep like this. Initially may start like this, right. After one move you may move right, sometimes you may move left. They can be 2 cells apart, right. After second move they can be 4 cells apart. After the ith move they can be I plus 2 cells apart or something like that, isn't it. Initially you start, after one move they can be 2 cells apart, the excess can be maximum. After one move you can move one cell to the right and one cell to the left. So, the excess can be 2 cells apart. After making the second move it can be 4 cells apart, after making the third move it can be 6 cells apart and so on. So, after I steps the distance between two x's will be maximum 2i. They can be 2i cells apart. So, you have to make one move this way, one move this way, isn't it. Not only that, some more moving right or left you have to make one or two moves again. So, if you move 2i cells to the right and then 2i cells to the left, you are making 4i moves. But while writing the excess you have to shift, while coming back, if it is a move right you will come back here and then put it here and go back, isn't it. So, it will be some things like not exactly 4i, slightly it may be more than 4i. So, maximum I will put is some ki, k will be, k can be between 4 and 6 for that matter. Anyway, it is finite. So, if it makes n moves with a multi-tape Turing machine, makes n moves, single tape Turing machine, how many moves it will make? It will be sigma I is equal to 1 to n some ki, k is a constant, right. So, it is order n squared moves. So, summing up will be I into I minus 1 by 2. So, k into I minus 1 by 2 or I plus 1 by 2, I into I plus 1 by 2. So, it will be order n squared. Constant does not matter. So, while simulating a multi-tape Turing machine, the single tape Turing machine makes quadratic number of moves. So, this simulation does not affect the polynomial property. If something is accepted by a multi-tape Turing machine in polynomial time, it will also be accepted by a single tape Turing machine in polynomial time. So, this is another generalized version, that is a multi-tape Turing machine. The third is non-deterministic Turing machine. What is a non-deterministic Turing machine? So, instead of delta of QA, you may have a finite choice P1 A1 R, P2 A2 L, P3 A3 R and so on. Some finite number of choices will be possible for each move. When you are in state Q and reading a symbol A, then either you can go to P1, print a A1 and move right, or you can go to P2, print a A2, move left, or go to P3, print a A3 and move right. It is like this, but please remember that it cannot go to P1, print a A2, you cannot combine like this. The triples are specified, it has to choose from one of the triples, right. So, starting with the initial ID, you may have some choices, from each one you may have choices, from each you may have more choices and so on. So, when will the string be accepted? If there is one sequence which leads to acceptance, the string will be accepted. Other sequences may not lead to acceptance, does not matter. If there is one sequence which leads to acceptance, the string will be accepted. Just as we define for a push down automata. So, how do you simulate a non-deterministic Turing machine with a deterministic Turing machine? How can you simulate a non-deterministic Turing machine with a deterministic Turing machine? Now, the idea is like this, there will be mappings for the non-deterministic Turing machine will be given like delta of QA, delta of PA, there will be some moves defined for the non-deterministic Turing machine. Now, for this, for example, there may be 5 possible choices, for this there may be 3 choices, for something like that there may be 2 choices only and so on. Take the maximum value, maximum of these choices. For one move there may be 5, for another move there may be 3 choices, for another one there may be 2 choices and so on. So, take the maximum value, maximum is R say, among this. Now, from the letter, from this consider sigma is equal to 1 to R and generate sequences over 1 to R in the standard ordering. We have studied lexicographic ordering and standard ordering, you remember. So, if you generate strings in the standard ordering, what will be the order? 1, 2, 3 up to R, 1, 1, 1, 2, 1, 3 up to 1 R, 2, 1, 2, 2. You can generate sequences over 1 to R in the standard ordering, right. So, in order to simulate a non-deterministic Turing machine with a deterministic Turing machine, the deterministic Turing machine will have a finite control and it will have 3 tapes. We are taking non-deterministic Turing machine to have one tape. You can extend the result when it has got multi-tape also. So, the non-deterministic Turing machine has one tape, whatever is there it is input, it is copied on here the first tape. Then what it does is, it copies the input onto the second tape and one by one it generates the sequence there. First it will be generate 1, then simulate the behavior of the non-deterministic Turing machine if I call as M1, the deterministic Turing machine which is going to simulate I call it as M2. M2 has 3 tapes, okay. So, in one tape the input is there, the second tape and the third tape are initially empty, second tape and the third tape are initially empty. You copy the input onto the second tape, then generate the sequence one by one. First you generate one sequence and then simulate the behavior of M1 by M2. You simulate, M2 simulates the behavior of M1 on this input using this sequence. Suppose at particular time the sequence is say 2, 5, 3, 2, 1 and the input is copied on here. The head will be pointing to that initially, no. So, in the initial state is Q naught. So, delta of Q naught A1, there will be 1, 2, 3, 4 choices say for this. The number is 2 here. So, it will select the second choice and behave like that. It will simulate the second choice on this. So, suppose it is moving right, printing something here and then the symbol read is A2, state changes to P say. Then the second move is delta of P A2, right. Now, delta of P A2, this has got say 1, 2, 3, 4, 5 choices, then this number is 5. So, it will select the 5th choice and simulate, right. Similarly, for the next move it will for that there will be some choices, it will select the 3rd. Now, it may so happen that for this there are only 3 choices possible, then number 5 is appearing here, that means it will halt. I mean it halt means it will discard that, it cannot simulate the 5th choice, there are only 3 choices for that, but the number 5 is here. So, it cannot proceed further. Now, once if it accepts, it accepts, if it does not accept, suppose after simulating the moves with this sequence 2, 5, 3, 2, 1, it finds that it is not accepting, then what it will do is it will erase again, the contents would have been changed by now. So, it will erase this, write the next number in the next sequence in the lexicogram, in the standard ordering, that is 2, 5, 3, 2, 2, something like that. Then copy the input again here, try to simulate with this sequence and so on. If the string is accepted by the non-deterministic Turing machine, then if suppose some string is accepted by the non-deterministic Turing machine, then there will be some sequence which leads you to acceptance, is not it. And when you are creating the sequence one by one here, at some time that sequence will appear here on the 3rd tape. Then you copy the input onto the second tape and when you simulate it will get accepted. So, if a string is accepted, it will be accepted through a sequence of moves, and that sequence will be a sequence over the alphabet 1 to R, right, and sometime or the other that will appear here, because you are going to generate the sequence one by one here. When that particular sequence appears here, you copy the input onto the second tape and simulate the behavior of M1 with this sequence, then it will accept. But if a string is not accepted, what will happen? If a string is not accepted, one string you will generate here, it will not get accepted, then you will try the next sequence, it will not get accepted, then you will try the next sequence, it will not get accepted, then you try, it will not get accepted, and so on. So, you will go on and on, it may not halt, machine may not halt for strings which are not accepted. For strings which are accepted, after some time that particular sequence in which it accepts will appear on the third tape, and when you are trying to simulate the behavior of M1 with M2 using that sequence, you will reach an accepting state. So, the string will be accepted. So, in this way the non-deterministic Turing machine can be simulated by a deterministic Turing machine, but how many moves it will take? Too much, is not it? Because if it accepts in n move, that sequence of length n has to appear here. For that you have to write sequences of length 1, length 2, length 3, length 4, length 5 and so on. How many sequences of length 1 will be there? It will be r, length 2 will be r squared, then r cubed, 1 by 1 r power n, 1 by 1 all these sequences have to be written here, and each time you have to simulate the behavior and so on. So, the number will be too much, it will be, the time will increase exponentially. You can simulate a non-deterministic Turing machine with a deterministic Turing machine, but the time will increase exponentially. Okay. But the language acceptance power is not changed. Whatever you can do with non-deterministic Turing machine, you can do deterministic with the deterministic Turing. Whereas in the case of push down automata, there are languages which cannot be accepted by deterministic Turing machine, but here any type 0 language can be accepted by a deterministic Turing machine, it can be accepted by a non-deterministic Turing machine. As far as language acceptance power is considered, they are equivalent, but the difference comes in the number of moves. So, this is another generalization. Another is multidimensional tapes. I will consider 2-dimensional tape. You can also have 3-dimensional tape. In fact, abstract way you can even think of k-dimensional tape. So, when you have a 2-dimensional tape, suppose this is the input A1, A2, A3, A4, A5, A6, A7, this is the input. The rest of them are blanks. The tape is infinite in this direction, in this direction, this direction, this direction, and the tape head will be reading one cell. After reading that symbol, it can change that symbol and then move left, right, up or down. So, the mapping will be from, it will be of this form, P, A, L, R, it can move left, right, up, down. Does it give additional power? Will this give additional power? But it will not give additional power, because this one, suppose this is the portion, non-blank portion, this is blank, this is blank, this is blank, this is blank, this is blank. So, this can be represented by say some hash blank A1 blank hash A2, A3, A4 hash blank A5 blank hash A6 A7 hash. This is continuation, same tape. You can write it like this, A6 A7 blank hash. So, the whole thing you can write as strings within the hash marker, each row you can write like this. So, if you are reading a symbol A5, the tape head will be here, and after reading A5, if you want to move left, you can move left or move right here without no problem. If you want to move up or down, how will you do? The tape, suppose after reading A5 you have to move up, you have to go to A3. How will you do that? In the second tape, there will be this can be contained in one tape. In the second tape, when you move like this, you have a counter which increments and say that you have moved 2 cells. Then when you go to the left one, if it is move up means left block you go, then reach this hash symbol, move 2 cells to the right, that will show that you have to be in A3. Is that clear? If you have to move from here to here, when you move this head in this direction, how many cells you have moved to reach this hash, you keep a count in another tape, and then move to the next hash symbol, then by the same amount of same number you move the tape head to the right. That means the tape head position is changed accordingly. Similarly, if you move down, instead of moving to the left block, you will move to the right block. That is one thing. Then suppose you are here and you move right, that means you have to add a column, one more column. You may have to add one more column or one more row or up or one more row left. If you are going to add one more row up, you have to create one new block on the left. If you are going to create one more row down, you have to create one more block to the right. If you are going to create one more column to the left, each block you introduce one blank and use the technique of shifting over. We know how to shift the symbols to the left or to the right. Make use of that and create one blank symbol in every block to the left. If you are creating one column to the right, shift again and then create one blank at the end of the row. So, whatever you can do with 2-dimensional tape, you can do with 1-dimensional tape, but the number of moves will be more. Please remember that it will not be just, but it will not be exponentially increased. There will be more moves if you want to, especially if you want to create a new column, you have to do a lot of things, but it will not be as bad as simulating a non-deterministic Turing machine with a deterministic Turing machine. So, this is 2-dimensional tape. You can have a 3-dimensional tape where you can move left, right, up, down or this way or this way. 6 possibilities will be there. In an abstract manner, you can even think of k-dimensional tapes. This is another variation. Then multi-head Turing machines. This you have only one tape, but there may be many heads. Three heads reading the symbols A, B and C. Now, depending on the symbol read state, again the move will be like this: delta of Q, A, B, C is some A, move right, B, move left and so on, C, move right. So, depending upon these symbols, it will print a A and move right. If it print a symbol and move left, print a symbol and move right and so on. Now, how can this be simulated? multi-track, again the same idea of multi-track. If you are having k heads, you will have k plus 1 tracks. Suppose I have 3 heads, input will be there in the first track and the tape head position will be marked, first tape head position will be marked in the second track, second head position will be marked on the and so on. Again in a similar, making a left to right move, right to left move, we can simulate the behavior. There is one small point you have to note here. What is that? If there is a conflict. Suppose tape head 2 and 3 read the same symbol, then which one will you follow? Move up the second head or third head? But rewrite and move right. Head can move left or right, does not matter, but a symbol rewriting, how will you do that? You must specify some priority in that case. Second head will have higher priority than the third one and so on. Some priority has to be specified. So, you can simulate a multi-head Turing machine with a single head Turing machine. Then offline Turing machines. What is an offline Turing machine? Offline Turing machine is a Turing machine where the input is given in one tape and it is read only. There is one tape which keeps the input with n markers and there will be other, it is a multi-tape Turing machine. There will be other tapes, but the input is read only. We can only, this on this tape the head only moves this way. It cannot move beyond this, it cannot move beyond that. Other tapes you can do for computation, right. So, this is a particular case of a multi-tape Turing machine, is not it? So, obviously it can be simulated by a single tape Turing machine. Another thing is, whatever you can do with a single tape Turing machine, you can do with an offline Turing machine, any Turing machine is, you have the input and then one more tape. Suppose there is a multi-tape Turing machine with k tapes, to make it offline, have a Turing machine with k plus 1 tapes. Copy this onto this input, then afterwards you do not bother, while copying only use this, copy this onto this and in this k tapes you simulate the behavior of the first machine. So, you have a Turing machine with k tapes M1, you want to make it offline, M2 will have one more tape which contains the input. First stage is to copy this input onto this, then just behave like M1. If it accepts, it will accept, if it does not accept, it does not accept, right. So, this way you can simulate a simulator of any multi-tape Turing machine by an offline Turing machine. Now, these are some of the generalized versions. See, you are making the machine more general and then you are saying that it still is equivalent to the basic model. Now, you can also have a restricted version, some restricted versions of Turing machines which have the same power as the original Turing machines. We shall consider them next, and also you can look at the Turing machine as a generating device. So far we have considered the Turing machine as an accepting device or a computing device. You can also look at the Turing machine as a generating device. You have a tape, output tape, in which one by one the words will be printed between some marker symbols. And because you are able to do that, that is why it is called a recursively enumerable set. The language accepted is usually called a recursively enumerable because you can enumerate the strings using an output tape. Okay. So, we shall study about this later in the next lectures. So, we have seen that there are several generalized versions of Turing machine. As an example, we will consider a Turing machine with a 2-dimensional tape. The problem is like this: construct a Turing machine M with a 2-dimensional tape, and it has the input like this, a row of n x's, and finally you want a pattern like this, that is the row of n x's is preceded by a row of n minus 2 x's and followed by a row of n minus 2 x's. So, you want to generate this pattern from this pattern. This is our idea, and you want to construct a Turing machine for this. We know that a 2-dimensional tape Turing machine has got 4 types of move. Depending upon the state and the symbol read, it can move left, it can move right, it can move up, or it can move down. 4 types of moves are possible. So, with this idea, let us see how we can obtain this pattern from this pattern. So, the corresponding Turing machine has 12 states, Q0 to Q11. Q0 is the initial state. We use 3 symbols, x, y and blank. X is occurring in the pattern. The blanks are denoted by dot in the figure. In the 2-dimensional tape, we denote by a dot the symbol blank. The mappings are given by this. We will see how we are using the mappings. So, some more mappings. These are the mappings which define the moves of the Turing machine. So, let us consider a pattern where you have 4 x's initially. The machine begins in this position in the state Q0, and it ends here after printing 2 x's above and 2 x's below. So, it ends up with this pattern, and the halting position is this. It starts with the initial state in this position. Let us see how we get this pattern from this pattern. So, initially we have this position, the tape head is here, and the mapping used is delta of Q0 x is equal to Q1 y r. So, it changes this x into a y and moves right. So, now the tape head is in this position. The second mapping is delta of Q1 x is equal to Q2 y u. The second x, it changes this into a y and moves up. So, the next situation is this: x has been changed to y and the tape head is in this position now. Now, we want it to print a x here, we also want to print a x here. Let us see how this happens. Now, the tape head is here and the state is Q2, the move is given by this mapping. Delta of Q2 blank is Q3 xd. So, it prints a x over this blank and then moves down. So, the next stage it prints a x here and then moves down. So, the tape head position is here now. So, the tape head is here and the map use is this: delta of Q3 y is equal to Q4 yd. It does not change this y, but then moves down in state Q4. So, tape head position is here, and in Q4 it reads a blank here and then goes to state Q5, changes the blank into x and moves up. So, at this stage it prints a x and moves up here. So, in this column it initially changed the x into a y and then moved up, printed a x, moved down, again moved down, printed a x, and it came to this position. Now, moving to the right, it does the same thing in the next column and in the last column also. Though we do not want x, initially it prints a x and then afterwards it erases this x and this x. So, moving to the right and repeating the same thing, it prints a x above this and below this, changing the x into a y. Similarly, changing this x into a y, it prints a x above and a x below. Now, when it moves right, it does not see a x, but it sees a blank. Now, it knows that it has come to the end of the first row of x's, and so it moves left and erases this x and erases this x. So, that is done by this mapping. When it sees a blank here, it moves left and then it moves up and then it erases this x using this mapping, coming down here and then going down here, it erases this x and goes up. Now, these two x's have been erased and the tape head is here, but this whole of this is y and we want to change the y's into a x. That is done by this mapping, the last one. And so, after changing the y's into x, we get this pattern. In Q10, it changes the y's into x, moving left. It keeps on doing this, and when it sees this blank, it knows that it has exhausted the rows with which it started, and so it halts at this position and halts on seeing a blank. Thus, the final pattern is this. This way, we can get a pattern from another pattern. This is a very simple example just to illustrate how a 2-dimensional tape Turing machine works.